So let's continue talking about implicit differentiation. What we learned first was if we wanted to take the derivative with respect to x of x to the fifth, we could just write what? 5x to the fourth. And since this base was x and we're differentiating with respect to x, there's nothing more that we need to do. We're done. Okay? But then we learned that we could still use that idea of taking the power out front and subtracting 1 from it, even if the base wasn't x. This is not x. As long as we do what? Multiply times the derivative of whatever it is. That's the whole idea of the chain rule. So we would bring the 5 out front, leave the base the same, 2x plus 3, to the fourth, just like we did a minute ago. But to compensate for the fact that that wasn't an x, we multiply times the derivative of what it was. So that's 5 times 2x plus 3 to the fourth times what? 2. So we end up with a coefficient of 10 instead of 5. All right, now that is the chain rule that we learned previously. Now what I want to talk about today is the same idea just with a different variable. So here again, we want to take the derivative of something raised to a power. The problem is this something, the base, is again not x. That's okay. According to the chain rule, we still bring the 5 out front. We leave the base the same. We subtract 1 from the exponent. But to compensate for the fact that that wasn't an x, we multiply by what? The derivative of whatever that base was. The derivative of y. But the way we write it is 5y to the fourth dy dx. Implicit differentiation is referring to taking derivatives when the y's are all mixed in with the x's. And so what happens is you get terms like this one. You have to take the derivative of that term, and you just use the chain rule to do it. So every time you take a derivative of a term with a y, guess what? You're going to have a dy dx. Let's practice. Okay. All right, so on the left here, I have the explicit form of the function y equals 1 over x. That can also be written implicitly as x times y equals 1. You agree those are the same function? Okay. There are a lot of functions that we don't have an explicit way of writing. We can't get y by itself, which is the reason why we often will need implicit differentiation. But I just wanted to demonstrate for you that if I take the derivative the way we just discussed using implicit differentiation, I'll still end up with the same answer in the end. So what I'm going to do, though, is when I say implicit differentiation, you should be thinking take the derivative of both sides. That's basically what it comes down to. So I'm going to take the derivative with respect to x, my goal being to find dy dx. That's why I know I want to differentiate with respect to x. I'm going to take the derivative with respect to x of xy, and I'm going to take the derivative with respect to x of 1. Those two are equal, right? xy equals 1. So the derivative of xy should be equal to the derivative of 1. When I take this derivative of x times y, it's a product rule, correct? What's the first function? X, and the second function is y, right? So I'm going to have the first times the derivative of the second plus the second times the derivative of the first. Okay, so what's the first function? X. And we're going to multiply that times the derivative of y, the second function, plus the second function's y, and we're going to multiply that times the derivative of x. And what's the derivative of 1? 0. Derivative of a constant is 0. Good. Okay, now let's go back in here and see if we can go a little bit further. The x is going to stay the same. What's the derivative of y with respect to x? Well, dy dx. That's what that means. And the y is going to stay the same, but what's dx dx? 1. The derivative of x with respect to itself is just 1. So what we have is x times dy dx plus y is equal to 0. Remember, my goal was to find dy dx. What's going to happen in these problems is dy dx is essentially a variable inside of a formula, and we want to solve for that variable. So how do we do that? We get the terms with the dy dx on one side, everything else to the other. So the first thing I'm going to do is move that y over here, and then I'm going to divide both sides by x to get dy dx by itself. So what does dy dx equal? Negative y over x. Now what we see here is when we use implicit differentiation, our formula for the derivative, our formula for the slope, is going to have y's and x's in it most of the time. Okay? And that's fine. But in this case, it's actually possible to solve for y in our function. A lot of times it's not. We know that y is equal to 1 over x, right? So to see that this derivative, negative 1 over x squared, is the same as this derivative, let's go ahead and replace y with what it's equal to, 1 over x. So dy dx is equal to negative 1 over x. And how does that simplify? Yeah, you're dividing by x, so you're going to have negative 1 over x squared. Same thing, right? So if I ask you to differentiate implicitly, though, this is the answer that you get. But I just wanted to show you that these are actually the same. If I ask you to differentiate implicitly, your answer would look like this. Your answer would look like this in red. Okay, but I was just proving to you that this, in fact, is really the same thing as what we got when we differentiated explicitly, the explicit form.
I hope you found this video useful. If you did, please remember to like it.